Hello everyone. So today we will be starting with the design of inverter and we will see how we can access Cadence. So pay a lot of attention. So over here, while conducting the experiment itself, I'll be giving out the steps, so you need to note them down. Now, the first thing first, Cadence cannot be operated from Windows operating system. Alright, it needs an open source operating system. So what we can do about that? So we have got a software, okay? The name is Xmanager Enterprise. It is like a virtual machine, okay? Now, this is the first thing that we need to take care of. So we open it, okay? We open Xmanager. Alright, now in Xmanager, the first option is that of an X browser. The first option is that of an X browser. So double click on X browser, okay? The moment you double click on X browser, what you can see is there are two folders, shared and Cadence. So we need to have the access for Cadence, so we double click on it, okay? The moment we do, we get inside of Linux. The moment we do, we get inside of Linux. Click on that file that you have extracted, okay? Double click on it. This will be empty for you guys at that time, okay? So I'll just click in the empty space provided and I will click on right click, okay? I'm doing here right click, open in terminal. These are all steps, okay? The moment you log in via your student ID and password, you will see a brown color folder named as studentname.tar.gz, okay? You have to right click and click on the option extract here. Right click, extract here. The moment extraction finishes, a folder will be created on the desktop, blue color folder only. Now in that blue color folder, the name of that folder will be student name. So what you're going to do? You're going to rename the folder according to your USN, okay? Then after naming that folder, click it open. You will see nothing there. Now right click, click on open in terminal. Right click and open in terminal. So you will get a pop-up like this, okay? You will get a pop-up like this, okay? What is this pop-up saying? Welcome to Cadence Tools Suite, okay? How come this pop-up knows that you wanted to access Cadence? Because you extracted a zip folder, okay? Now, one thing you have to note, that in any open source operating system, you cannot just click or do something to work. You have to provide commands. You have to provide commands on there, okay? Now I want to use Virtuoso. Remember in our first class what did I say? Which was the tool for analog? The tool for analog design was Virtuoso. What was the spelling? Virtuoso, okay? Spelling of that tool is very important. That's why I'm stressing on that, okay? Now to access that tool, did you see any icon in the desktop that I've shown right now? I'll show you again. Can you see any kind of icon that looks like some kind of a tool? See, I'll show you here. This icon is for whom? I see Xilinx. This is icon for whom? Microsoft Edge. Okay, this is for Xilinx Plan Ahead, right? This is for Skype. So what do we do till now? We just double click on the icons and work is done, right? But in Cadence you can't do like that. In Cadence you can't do like that. Okay, now and what did I say? In open source operating system you cannot just double click and get the things done. Okay, so you have to give a command, right? So what is the command? To invoke the tool. Invoking means trying to access. Okay, invoking means trying to access. So I want to invoke Virtuoso. Okay, so I will type VIRTUOSO, VIRTUOSO space ampersand, space ampersand. Okay, I'll just maximize this pop-up. So this is the command I want, Virtuoso space ampersand. That ampersand symbol is required to mount the tool. What is that mounting and all? You don't need to go into such details. Just remember the command to invoke analog tool, that is Virtuoso, is Virtuoso space ampersand. Now if you while writing Virtuoso, if you make a mistake in the spelling, you will get error. Okay, so spelling is very important first of all. Now once I have written all those things, Virtuoso space ampersand. Ampersand means what? That and symbol. Okay, now click enter. Click enter. So you see Virtuoso design environment has been invoked. Okay, now after this, can you see I'm getting this window overview? What's new in this version? So this is our version of Cadence. Cool. Now this is an overview. What all new things are there? What all previous things was there? Do I need to know all those things? No. So I will close this window. Not required. That overview window is not required. Alright. This rectangular box, can you see this? What is the name of this box? It says Virtuoso. So this is the tool that is of importance. This is the tool that is of importance. Okay, do not maximize this this window. Okay, do not let it be in this small rectangle only. Otherwise you while closing everything, you will close this window also, then you will be out of Virtuoso. Don't do that. So let it be in the shape it is. Okay, let it be in that rectangle shape only. Do not maximize this window. Now from here I can see 4 options are there: File, Tools, Options, Help. Alright, so I will click on File. I will click on File. These are the steps. Note them down. File. From File, first option, New. First option, New. Okay, I haven't yet clicked. So listen why it is required. Now can you see there are 2 options from New: Library, Cell View. Library and Cell View. Okay. Now in your VLSI lab there are 2 sections: analog and digital. Analog and digital. So now if that is the case, then analog has a set of experiments, digital has a set of experiments. Okay, so now in that what you can do is, like, instead of creating each experiment separately, it looks nice when I create them under one big folder, just like a library. What is a library? A place where several books of different backgrounds and different categories are kept together, right? So I will create a library first. This is very important. Okay, now this library that you will be creating will be the place wherein you will be saving all your experiments, will be the place wherein you save all your experiments. So this is important, right? So I will create a library. So what were the steps involved till now? File, New, Library. The moment I click on library, I get this window, new library. Okay, so over here I'll give my name. Okay, you need to provide your own USN. You need to provide your own USN. Okay, don't give names, stick to USNs. Okay, now before I click OK, I have one more small step to work. What is it? This is on the left side, right? This naming and all. On the right side of this window, I can see something named as technology file. Remember in our first video, what did I say about technology file? Technology file means nothing but the channel length. And I had also mentioned that before designing anything, the designer in VLSI will fix the technology file. Okay, will fix the technology file. And how many technology file is provided by Cadence for us? 3. 180 nanometer, 90 nanometer, 45 nanometer. And in our syllabus, which technology file is to be attached? It is 180 nanometer. Okay, so can you see the third option over here? What does it say? Attach to an existing technology library. Attach to an existing technology library. So I will click on it. Alright, then I will click on OK. Now since I have clicked on the option attach an existing library, so it is asking which library you want to attach. Okay, so I need 180 nanometer. Alright, so I will scroll down. Can you guys see GPDK 180? Remember, the library files are named as GPDK. Okay, these are all generic library files which gives us an estimation of our output. And estimation is also not like if the answer should have been 99, you will be getting 90. So we can say no, not like that. Okay, if the answer should be 99, you will be getting 98.9999 kind of an estimation. Okay, so this is good for the scholars, the students and researchers. So I'll click on GPDK 180. Can you see GPDK 090 over here, GPDK 045 over here? So like for research purpose, you can go for 45, 90, whatever it is. But for VLSI Lab, we will stick to GPDK 180. Clear? Now I'll click on OK. Now I will click on OK. Okay. Now see what this Virtuoso tab is saying. Design library with my library name successfully attached to technology library GPDK 180. Clear? You've created that space. You have brought in the racks. Okay. Now it is time to fill them with books. So that book in our case is nothing but the experiments we are going to do. So again, alright, after attaching the library file or technology file, click on File. First option is New. Click on it. Then from there, do I need to create another library now? No. So I will click on Cell View. Cell View is nothing but the file that will be required to create your experiments. So File, New, Cell View. Click on Cell View. Now see, library, your name, that particular USN should be there. If it is not there, no need to panic. Just drop it down and select the way I did just now. Okay, so no need to panic. Then it is asking in this library, what is the name of your first experiment? Cell means that first experiment. Okay, our first experiment is that of an inverter. Okay, so I will write inverter. Now all of us are very creative in our own life, isn't it? So when it comes to naming our files, we have a creativity extent of infinity, and we will name it randomly, isn't it? Which is to be avoided. Stick to the names of the experiment. So if it is an inverter, name it as inverter or INV. If it is a common source amplifier, name it as CS amp. Okay. If it is a common source, a common drain amplifier, write it as CD amp. If it's a differential amplifier, name it as diff amp, like that. Okay. So that later on you know which file corresponds to which thing. Okay. So naming of the files, please don't use your creativity. Stick to the device you're designing. Alright. Now pay attention over here. What kind of view it is saying? Schematic. Okay, this will come in handy later on. Alright. So I have named my file. I have seen which kind of view. Everything is fine. I'll click on OK. This pop-up comes in my system. It will not come in your system. So no need to think on this one. Okay. This is just for my personal system, not for your lab systems. Okay. So I have got something new. Now I will maximize this window. This is what I want. What does it say? Schematic L editing. Name of your library and the cell view. Okay. So this black screen over here with a lot of dots. Okay, this is the editor screen wherein we are going to design. Okay, so for an inverter, what all things are required? 2 MOSFETs, 1 PMOS, 1 NMOS. Excuse me. 1 PMOS, 1 NMOS. Now, I need them, right? They are the basic components. So once I have those MOSFETs, then and only then I can interconnect them to form an inverter, right? So what I will do, I will have to bring them out. Okay. So they are components. Okay, they are components. So I will press I. Okay, I for ice cream from keyboard. Now I am getting this add instance. That I is the shortcut for the term instance. What is an instance? Instance is nothing but a component. Okay. So now I need a MOSFET, right? Now here it is the first thing it is asking, library. Just now we created our library. Do we have anything over there? Nothing now. So I have to access some pre-existing libraries that will be having our MOSFETs. Okay. So I will click on browse. Alright. I'll click on browse. Now see, our library is over here. Set of libraries are there. Okay. Now from here I will click on which technology file did we add? GPDK 180. I'll click on GPDK 180 once. Okay, once only, not double click. Now, see, this is the library set column. On this set, the moment you click, these things appeared, right? So in this library, these are the cells. Clear now? So now, in this cell, what do I need first? See, this is the search option over here. Okay, I need an NMOS. Okay, so I'll type NMOS. So I'm having this NMOS with me. There are several other things with several other variations of their capacities. Okay, I don't need all those things. I just need a simple NMOS for the time being. Okay, so the moment I click on cell, on this particular cell, I am getting the third column also, view. Which kind of view do I need? I need the symbol. Okay, symbol of my NMOS. Clear? Now I'll click on close. So what did I do? I pressed I I for instance from the keyboard. I got a window. Over there it asked, first option is library. I clicked on browse. From that, the moment I click on browse, I got a window. Now make a note of this. To get the transistors, MOSFETs, okay, you need to click on the technology file that you have attached. So the technology file is 180 nanometer. Okay, so I single clicked on that. Then in the cell I searched for the component I want. So I typed NMOS, I got it. Now in the view, if nothing is selected, you have to select on symbol. Okay, then you will click on close. There is a tab over here, not that one, not this red one. Okay, this thing over here, bottom left corner. Click on close. Now see, what is this? Add instance saying library is GPDK 180, cell we selected as NMOS, view also we selected as symbol. Okay, now this is the characteristics of the NMOS we have selected. This is the characteristics of the NMOS we have selected. Now this part, alright. So length means which length? The channel length of the MOSFET. So by default it will show 180 nanometer. See, 180N. Okay, 180N. So do we need to change that? For the time being, no. But when we are doing research, yes, you have the option of changing this also. Okay, you have the option of changing this also. But the upper limit has to be, okay, it has to be 180 nanometer only. The limit has to be 180 nanometer. Okay, like if I am using 90 nanometer technology file, like GPDK090 file I have attached, so by default it will say 90 nanometer, but I can type over there 65 nanometer also. Okay, now that is a different thing. When we do research, that is a different thing, but we should stick to our syllabus. Alright, so we'll leave this channel length to 180 nanometer only. Now total width. Okay, total width and finger width, two things are here. Okay, the moment I change one, the other will also change. Okay, because the number of fingers are 1. What is this? How is this? This I will tell you later on. Okay, but for the time being, for our syllabus, we shall stick with fingers equals to 1. So now this is the default value for 180 nanometer. Width the default value is 2 micrometer. If you want, you can change it. Okay, U it is written. Okay, 2U means 2 micrometer. Alright, so let us keep NMOS with the default width of 2 micrometer only. Okay, click on hide. The moment you click on hide, where can you see at the end of my cursor one MOSFET is revolving, yellow in color, means I have not yet placed it. Okay, so I will place it somewhere over here. Single click. Do I need another NMOS? No. So I will press escape. I'll press escape. Now see, this is an NMOS. How many terminals? 4 terminals. MOSFET has 4 terminals to it. Okay, W:2U means width of this NMOS is 2 micro. L:180N means channel length of this MOSFET is 180 nanometer, and the name of this instance is NMOS 1. Okay, see, NM0. Why 0? Because only one NMOS is being used. If I would have had another NMOS in this design, that another one would be named as NM1. Okay, okay, so I have placed the NMOS. Now what else do I need for the inverter? I need a PMOS. Okay, so that is another component, another instance. So what should we do? We should click on I from keyboard. From here, what did we do? Browse for library. Click on GPDK 180. I need a PMOS, so I will type PMOS. PMOS is selected, symbol is selected, close. Now in this, again channel length is 180 nanometer. Now over here total width is 2 micrometer. Width is 2 micrometer, default value it is showing. But can we use PMOS with the same width as that of an NMOS for inverter? Yes, we can use, but we will get a slightly different output than the actual one. What did we study in VLSI and 6M? That the width of PMOS should be 2.5 times of that of NMOS, right? So 2 into 2.5 is how much? 2 into 2.5 is 5. So I will select this whole thing, 2UM. Select the whole thing, press backspace, type 5U. No need to write space capital N. After writing this, click over here. Can you see it is automatically taking the measurement? Alright, now click on hide. Click on hide. Okay, now I am getting the PMOS, so I'll place it over here. Alright, I'll place it over here. Do I need another PMOS? No, so I'll press escape from keyboard. I'll press escape from keyboard. Now you can see W is 5U, L is 180 nano, and it is named as PM0 PMOS, and it's the first instance we used, so 0. So I placed the components. Right now I need to connect them. So how to connect them? By a wire, right? So I'll press W. I'll press W from keyboard. W for work. So click on W. Can you see this thing changed over here? Something tagging along with the cursor. Yeah, looks like a wire. Okay, so wire is activated. Now can you see the moment I bring over here, it is becoming yellow in nature, right? So single click over there, single click over here, and single click over here. So if I am connecting from port to port, this red to this red, single clicks. Okay, but now see, you can connect either like that in this fashion, or directly you can connect from port to port. It's your choice how you want your design to look. Okay, why did I connect both the gate terminals? Because gates are clubbed together for inverter. Now see, what did I do? Gates are clubbed, but input has to be connected somewhere, right? So single click on this wire, bring it outside, okay, to a particular distance, and then double click on the black screen. Done. The wire ended over there. Okay, now drains should be clubbed together, so I'm clubbing them together. Okay, same thing, from this clubbed drain output should be driven. So again double click on the black screen to end the wire. Okay, now VDD has to be provided to PMOS, so I have brought a wire out for that. Ground has to be connected to the source of NMOS, so a wire for that. Now what about this middle terminals? They are the body terminals. Now body for NMOS should be connected to whom? Should be connected to its source, which is connected to ground. Body of PMOS should be connected to its source, which is then connected to its VDD. Okay. Done. Okay. Now wiring, everything I have provided the wires with. I'll press on escape. I don't need a wire anymore, so I'll press on escape. If I want another wire, I'll simply click on W. Alright, now this is the schematic. Okay, can you see over here? Inverter schematic means you are creating the first stage. There were 3 stages in analog, remember? First was to create the schematic, second symbol, third was the test circuit. So you're creating a schematic. Okay, in schematic we are not going to provide the voltage sources. We are only going to provide pins for those input and output terminals. Okay, so over here I need to have an input terminal, so I'll provide a pin over here. To get a pin, I will simply press P. P for pen. Okay, P for pen from the keyboard. Now I need to have a proper name for it, so I will write V in. Okay, direction, this is very important. Okay, it has to be an input pin, so I am selecting it as input only. Clear. Now I'll click on hide. Can you see something has been attached? And can you see a small square box at the end of this part? Small square box. Okay, that part has to be connected to the wire. Okay, point contact. Click once, done. Name has also come. Now I need an output pin. I will press P again. Okay, so name for that is V out. What do I need to change? The direction. So I'll click on output. Done. I'll click on hide. Now see, that small square box is at the back of this pin. So that has to be connected. That square box has to be brought at direct point contact with the wire. Click once, done. Clear. What else is required? This VDD and ground, right? P. Now VDD, and because both are power rails, VDD and ground, remember they are called the power rails, so I can name them together, VDD space GND. Now one thing you need to remember, the moment you are doing multiple namings together for pins, do not use comma, use space. Single space, Cadence will understand, okay, I am naming multiple pins. Now what about the direction for this power rail? Is it input or output? Can we say whether it's input or output? No, na? But they are power signals, so I'll click on input output. Till this point, did you notice something? Until what this it is input or output, the signal type was signal. Okay, the moment I clicked on input output, it changed to power. Okay, just to show you I had to select it again, but if you go back to this video you observe this point, you will see for both V in and V out the signal type was signal. The moment we clicked on input output as direction, it became power. Now click on hide. Which pin did you name first? VDD space ground, right? So the first pin will always be VDD. So first I will place, now see the square box is inside this and it looks kinda different. Okay, then what was the next pin named as? Ground. Then I will bring it down. Okay, the way you are naming your pins, that is the chronology Cadence will follow to place them also. Okay, do I need any more pins? No. I'll click on escape. done. So this is the schematic we want. This is the schematic we want. Now we want to save this. See, this asterisk mark on top of this file is there. That means it hasn't been yet saved. Now see, this symbol everybody knows is for save. Beside that, can you see another thing? That same symbol but with a green tick. What is it written? Check and save. Means what check you're doing? You're going to do electrical check. Okay, electrical check, whether there is any wire that is floating, any pin that is not been connected, like that. Okay, so every time do check and save. You click on this option. Either you click on this check and save option from here, or from keyboard you can do Shift X. Shift X will also do check and save. So our schematic has been created. This is our schematic. So first option is done. Alright, first option is done. Okay, so in our next session we will create the symbol and we will do the test circuit. Alright, thank you.